Hi everyone, thank you for inviting me here. So I'm Georgia Atkinson from Newcastle University. So I'm part of the Cloud Computing for Big Data CDT, which is sponsored by the APSRC, and also one of the funders is Red Hat as well. So that's how I'm linked to the company. So as I said, I'll talk to you about the acoustic identification of cetaceans. So firstly, I'll just give you a brief outline of my talk. So I'm going to give you some background information, so just explain what cetaceans are, why they're important, and how you identify them. Then talk to you about the data that I use in my work. Then talk about the current state of being able to detect the audio that I need to detect. And then talk to you about the challenges in my future work. So firstly, background information. So what are cetaceans? So they are a subgroup of marine mammals. So they're made up of toothed whales, which are things like porpoises, dolphins, and some forms of whales, so things like killer whales, whales that have sort of physical teeth, and also baleen whales. So these are whales such as grey whales, right whales, and humpback whales. So these are the types of whales that are filter feeders, so they sort of have like bristles for the teeth instead of like physical teeth. And so why are they important? So typically they're a top predator in their habitat. So when you're in the sea, not many things really eat whales or dolphins or porpoises. So you can assume that a dolphin is your top predator. They eat some form of fish, they eat smaller fish, and it goes all the way down to the bottom where they eat sort of like kelp and sort of small organisms. And because of this, it's actually really good for being able to model the ecosystem within the ocean. So, you know, if the dolphin population are doing good, then they're growing every year, they're having a lot of young, they're quite healthy, not a lot of them are dying, then you can assume everything underneath is also doing pretty good. But on the reverse side, if, you know, the dolphin population is decreasing every year, so maybe they're not producing young, they're sort of getting disease, they're dying of starvation, then it's an indicator that everything underneath them in the habitat is not doing so well. So this is really important at the minute, especially because of things with climate change. So you need to see how sort of the ecosystem's changing with the warming sea temperatures, and also to do with like pollutions, sort of things with like plastics and things from like fertilizers and chemicals that are also polluting the seawater. So how do I identify them? So the many species in the cetacean family are just identifiable either visually or audibly. So on your left we have a bottlenose dolphin, and on your right we have a white-beaked dolphin. So visually you can see that the bottlenose dolphin is typically all grey, and the white-beaked dolphin, these all have sort of like white body markings on them. And also the faces are sort of different shapes, so you can actually tell the difference between them visually. And then audibly, if you can hear if they're going to play. Okay, so that's the white-beaked dolphin whistle. So it's very loud. Yeah, so the sort of three sort of high-pitched noises at the end were the noises from the white-beaked dolphin. And the one from the bottlenose dolphin sadly isn't playing, so we'll leave that. But yeah, they have a sort of higher pitched whistle, so you can tell the difference between them. But interspecies identification is a lot more difficult. So this is trying to identify sort of an individual within a pod. Visually, you typically do this by relying on markings or scars on the body and the fin. So if they've been injured from like fighting or boats have hit them, they get these marks, that scars, so you can actually tell them apart. And sometimes they're sort of born with birth markings, so you can use them to identify them as well. An acoustic identification, which is what my project is on, relies on species having individual calls, so you can actually tell the difference between them. I don't know. Ooh. Going back onto the other slide. Yes, so you can actually, so we need to have some form of acoustics where you'll be able to tell, okay, this is Jeff, this is Susan, so it's like their names. So what data do I need? So I need some form of acoustic recordings, so I use hydrophones, which are essentially underwater microphones, to do this. We need to record some form of cetacean that has some form of identifiable acoustics. And importantly, we need to be able to get more than one recording of that cetacean family and potentially the same group as well, because if we only say there's a whale, a right whale comes past and we record it, that's great, but if we never see a right whale again, it's going to be very difficult to be able to actually identify. So what data is collected? So we have underwater recordings of 2 different dolphin species. So I have a white-beaked dolphin, which is what this image is of, and also a bottlenose dolphin. We'll record them using the hydrophone, which is the sort of the black device here that you can see. It's attached to the white pole and then a weight at the bottom. And these dolphins make different vocalisations, so they make echolocation clicks, which are like sort of sonar that they send to be able to determine prey, find where prey are and determine what objects are, because the sonar pings back to them so they can tell the sort of shape. And they also produce whistles, and most importantly, they produce signature whistles, which is what I'm interested in. So these are whistles that they produce that they call them as like their names. So it's as if like me saying to this group, just saying Georgia, Georgia, Georgia. It's to do with the pod, so they can actually stay together, so they know that they're not going to vary from each other. And they appear yearly in the area that I do my research. So the white-beaked dolphins are typically here between June and October, from studies that were found, and the bottlenose dolphins seem to appear all year round. So how is the data collected? So I've got a nice cheesy animation for you. So imagine you're in the sea, and you're on a boat, and the boat that we go on is not much better than this boat. It has an engine, but that's pretty much it. So you're traveling along the sea, and then you want to look out for dolphins, and then you find some, and we get very excited. Take lots of pictures for the marine biologists so they can catalogue them visually. We then drive ahead of the dolphins, turn the engine off, and throw a hydrophone into the water. So we turn the engine off because in the past when we've done this and we've left the engine on, all you can hear is boat noise, so all the recordings are just useless that we'll have. So as I said, we'll do extensive fieldwork. We'll do that over the summer months. So we'll do that in the North Sea. So we'll have, this is the northeast of England. So Newcastle, where my university is, roughly like down here. So we survey this area here, which is in the red, and we do that over the summer months. But a lot of the time, we don't get out that much because the British weather's not that great. So we only really do about 30 days of surveying overall. So to get over that problem, we also introduced long-term monitoring. So we'll have 3 hydrophones in these places here that are left out for 3 months at a time to collect audio. So I have approximately 9 months of continuous audio feed from those 3 hydrophones as well. And we also did an experiment with this thing called a wave glider. So we did this, it's about 70 kilometers sort of northeast of this area, surveying an area twice the size of this in this area called the Farn Steep. So we did this because this is where the white-beaked dolphins typically habitate, but we can't get out there on our boat because we don't have enough protection. And this is what a wave glider is. So it looks a bit like a surfboard. On the top has it has hydrophone connected to the bottom of it. It has solar panels on the top to keep the engine, to keep it the energy. It doesn't have any form of engine, so the waves actually move it by these sort of propellers here, and then we have a rudder that way you have to move. And this needs to be manned 24 hours a day, so I had a team of 7 people who were going and checking this every probably 10 minutes or so, just because where we were going to survey, there was a lot of fishing activity and we didn't want to crash into a boat. So what is the current state of detection? So before we do any form of detection, typically audio needs to be pre-processed first. So it's normally processed into images. So we'll do this using some form of Fourier transforms, and these are known as spectrograms, which I'll talk to you about next. And we also do some form of filtering techniques. So we do filtering techniques just to try and remove some of the noise that is in the audio clips. So what are spectrograms? So when you get the audio, it looks like this. So you have time and amplitude, and this is the sound clip. Oh, it's not playing. So it's like a sound clip of a whistle. And you transfer that into a spectrogram. So instead of going from the time domain to amplitude, you now time frequency, and the colour depicts the amplitude. So the darker blues depict a low amplitude, and the reds and whites depict a high amplitude. So you can see here in this spectrogram, you've gone from not really knowing where the whistle is in this clip to actually being able to visually see it. So you can see that there's a fundamental frequency of this whistle, and then you have its overtones as well, which give it its characteristics. Yeah, so you can sort of hear like the wobbly noise is the whistle sound. So detection. So as I said, I've got over 9 months of continuous audio feed without any labels. So I firstly just needed some sort of simple and fast method to try and detect the whistles, because I thought if I listened to 9 months of continuous audio, I'm going to go crazy. And also probably start speaking dolphin by the end of it. So I'd first done some form of signal processing techniques. And also, I used local Facebook groups, dolphin watch groups, to try and find potential clips within this 9 months of continuous audio where there might be whistles. So these are the sort of posts that you get. So you have some people who are sort of like die-hard dolphin watch fans. They'll sit out on the coast all day with the binoculars. And they also get posts from people who are just out on the beach, maybe walking the dog or walking like with the family or something. So would take any location which is near the hydrophone. So here I've got Church Point, which is near one of the hydrophones. And they're normally pretty good at giving the time and the date, or we can get it from the actual post itself. So then would take an hour either side of this, so would roughly know, okay, in that 2-hour clip, potentially there's whistles in there. So the audio that I get from the hydrophones are split into 30-minute intervals. So the first thing I did was split this into 1-second clips. And then calculate the mean frequency spectrum. So what the mean frequency spectrum does is it calculates sort of what the average amplitude is over each of the frequencies. So the hydrophones that we have a sampling rate of 576 kilohertz. So you can detect any form of frequencies up to half of that. And we, as humans, can only hear up to about 20 kilohertz. So anything above sort of like here, we just can't hear anyways. So I then split this into looking just between 3 and 35 kilohertz, because this is the range that dolphin whistles are produced at. And that's the only thing that I'm interested in. I then calculated some form of threshold. So this was just to get sort of like the average amplitude of the noise. So I did this by taking the first 10 seconds of the 30-minute audio clip, splitting this up into the 1 second that I had, calculating this mean frequency spectrum for each of the seconds, and looking just between the 3 and the 35 kilohertz range, and then taking like the maximum amplitude. So for here, it would be this sort of amplitude here. Doing this for each of the 10 clips, 1 second clips, and then just average it. So we'll have some form of average noise. And then ran this threshold on the rest of the audio in that 30-minute clip. And if it ever spiked above that threshold, kind of assumed that it was potentially a whistle, because there is other things within the audio that is between 3 and 35 kilohertz. Like one of my main issues is boats. Boat engines have a really loud, prominent noise between 3 and 35 kilohertz. So a lot of the time, it'll just pick up boats. So I then visually check the spectrograms and listen to the 1 second clip just to see if it does have a whistle in it or not. And miraculously, this clip does. So I'll see if it'll play. Yeah, that's not great. So you can see that these two red lines are like the dolphin whistles. So these are potentially signature whistles, so you can see this of the same shape.
If you just turn your volume down on the laptop.
Okay. It's just coming up saying, giving us like a no. I'm not allowed to.
You are not able to do.
No. I do apologise. Oh, there we go, that was better. Yeah, so that's the dolphin whistle. So that's great, but it's also a problem, as I was saying, with boats. So sometimes if there's a prominent noise between 3 and 35 kilohertz for the whole half-an-hour clip, and I run my algorithm through it, I just get back that every 1 second clip's a potential whistle. So I know that there's something gone wrong then. It's just there's a boat being driven past, because there's a lot of fishing activity around some of the hydrophones that we have left out, and there's a lot of like towing boats and things like that, and fishing boats come about. So for that respect, my method's not great, and I might as well have just actually listened to the audio. So, and what we do with this result is I just save the timestamp of where this whistle is, so I can use it for future results. So what are my challenges in my future work so far? So I only have a small amount of labeled data. So when I was planning this talk, I did want to talk to you about using the spectrograms to be able to detect the whistles using convolutional neural networks, but I just haven't been able, sadly, to label enough data yet to be able to do this, but I'm almost, I think, at a point where I should be able to start using this. And the whistles are typically very quiet, and they're not visible in the spectrograms very well. So you can see in this spectrogram, we'll have a lot of noise, a lot of lines. These are typically, I think, the echolocation clicks, so the things that they used for when they're hunting. So I think this might be because they're trying to be able to determine what the hydrophone is, so they're like sending clicks at it to be able to see the size of it and see if it's potentially food or not. And you actually see there is a whistle very faintly in here, but it's very hard to see. And sometimes you'll be listening and you can go, oh yes, I hear loads of whistles. So sometimes, before I started doing the algorithm that I developed, I was just manually listening to the audio and like labeling some of the clips. But then when I was actually producing the spectrograms, you just couldn't see anything at all. And one of the other challenges that I face is not all of the whistles are signature whistles. So there's this method called SIGID that came out in 2013. So for bottlenose dolphins, to be able to determine if it's a signature whistle or not, you need to have 3 whistles of the same shape reproduced at least a second, no more than a second apart from each other. And all the other whistles are just for like socialization, I think. And potential future work. So I want to continue looking at methods for detection. So as I was saying, I want to try and use convolutional neural networks on the images to be able to detect the whistles. Possibly look into autoencoders as well. So if we can get an autoencoder that will just reproduce the noise, then we can look at the differences scores and be able to tell if, okay, there's an unusual point here that's not just noise, it potentially could be with sort of vocalisations from dolphins. And we also then want to move on to the classification stage. So for the classification stage, I'm going to have no labels to know, okay, this is Fred's signature whistle, this is Bob's signature whistle. So I'm going to have to use some form of like unsupervised learning method, possibly like clustering. And then my long-term goal for my PhD is to try and embed all of this system into some form of low-cost machine so you can use it in the fieldwork and also possibly in the long-term monitoring. So for the fieldwork, we want to be able to have this open source so any marine biologist will be able to use it when they go out in the field. So they'll be able to go out on the boat, throw the hydrophone in the water, possibly connect it up to a laptop with the software running, and they'll be able to know what group they're encountering. So that'll give them a good estimate of how they can tell how the population's doing. Also see, okay, this is Fred, how's he doing? And also, for the long-term monitoring, want to be able to embed it into the hydrophone so we can actually possibly do some form of tracking. So the engineering department at Newcastle University are building this thing called NanoPan, which actually live streams the audio back to base. And they want to produce like a sort of network of these out in the North Sea. So you'll actually be able to hopefully track where the dolphins are going and be able to see the sort of patterns, because at the minute we don't really know what they're doing. So thank you for listening.
Thank you. Do we have some questions from the audience?
Okay. While trying to detect which dolphin type it is, why haven't you tried to use unsupervised clustering methods just to get the hand of what they're seeing, or at least some sort of observation?
I just think for the minute, as I was saying, I just don't have enough labeled data to be able to do any of that. And I think the whistles, a lot of the whistles are very similar. So I think it would be difficult to try and use some form of unsupervised learning to say, okay, this is a signature whistle and this is them just saying something
Just
else.
unsupervised to see that it will cluster, do a clustering on his own without any labels. It's,
Okay. And
he will
just
try to
say-
detect some sort of patterns between similar things.
Okay, so just be
might
able to detect like
help
the
you.
whistles, right? Yeah, that's a good point. Thank you.
Next question.
Very wonderful talk. I actually sent just a picture home to my son who was interested in cetaceans. And finally, it's not just a boring computer science conference for him. So you just made my day. I'm sorry if this question might be a little bit ignorant.
I don't know, obviously.
But so you know Shazam, the app where you can like hold your phone.
Yeah.
They use fingerprinting, and obviously music. You know, there's still noise in the environment and
Yeah.
all that stuff. Have you thought about using an approach that's not machine learning based, or wouldn't that work at all because of the noise issues you're dealing with here?
Yeah, I think the noise issue is a real problem. So I think especially from the different environments I'm getting at, the noise is completely different in those environments as well. So I think I'm trying to look into more like signal processing techniques to remove that noise as much as possible. But I think that's as much as I've looked at so far.
Yeah, I was just thinking because with your goals you mentioned in the end, right? If you could do something that is non-machine, pure signal processing,
Yeah.
doing locally would be probably a lot easier because you don't need the compute power on that side.
Okay, thank you.